Well, it looks like we can start. Welcome back, everyone. So this is our last week. That's kind of exciting in a way. Congratulations on getting through all of it. I'm starting to run out of things to say. I don't even have too many announcements up here, but I'll turn it over to you folks first. Any questions at all or comments you want to start out with today? Okay, I kind of like the balance. We have three in person, three in Zoom, so that's a nice balanced design. So good representation. And no worries if you're going to come in later on YouTube or coming in through Zoom or anything like that. This is a really busy week. I totally understand. No judgment at all. So let's keep on going through the announcements. We're nearly done with chapter 21. It doesn't seem like that. We're still on the first problem, but these are actually pretty fast problems. The most work you put into this is really just absorbing the material, how the procedure works, what the hypotheses look like. But then beyond that, everything else is very, very similar to all of our other methods. So we're going to finish off this chapter. I don't have a homework assignment that goes along with it since it does not make sense to assign a homework assignment at this point of the course. Instead, there's going to be exactly one question from chapter 21 that will be on the real final exam. And I grade these knowing that it was the last content we looked at before the final with some understanding that you might not have had a lot of time to absorb it perfectly. That's okay. We'll still get through it. And I'll grade it in a way that reflects that. After we complete both examples in this section, we're going to move over to the review problems. I put here as a note that they've been totally modified at 2:43 p.m. today. I think that deserves some explanation. There were old review problems inside here, and they came from these, choosing a statistical method. But that was going against what I was saying earlier, that we're going to get some fresh problems. So I did find some time to actually put in some fresh problems. I typed them in really fast and just barely made them in before leaving for work today. So that's why it's been just suddenly changed. These are now fresh problems, and these are going to be the ones that we do take a look at. If you download these early, then you might want to take a look at the revised documents. So that's going to be our plan. Finish chapter 21, run through all these problems here, and that'll take us into reviewing on Wednesday. At the very end of the class on Wednesday, or maybe once we get to the last question or problem on there, we'll unlock the final exam, and it'll be right under where the red dot is currently. They'll just say hidden from students, and at the end of the day on Wednesday, they'll just become unhidden. We'll spend about 5 or 10 minutes talking about it, taking additional questions, and then that's going to be pretty much it for the course, at least the meetings. The final exam will be due on Wednesday, May 1st. I didn't put a specific time on that, so as long as it's in on May 1st, it's considered on time. I'm not trying to encourage you to send it in at 11:50, 8 p.m. or anything like that, but it'd be weird to say specifically at 5:30. I'm not going to be able to grade these at 5:30, so just as long as it's in on May 1st, it's considered fully on time. Any questions whatsoever, folks, with any of those announcements? Okay, well, let's get started then. We are just about through chapter 21. And before we go to where we left off, let's just take a look at the notes once more, just to kind of orient ourselves. We're going to come back to the conditions very, very shortly. But the reminder is, if you're doing the chi-square test for a one-way table, that means, as this is indicating, there is more than one population proportion. If there's exactly two, you're probably in chapter 20. But if there is more than two, we have to use the chi-squared procedure. So your null hypothesis is going to look about like this. Alternatively, we'll say at least one equation fails. And all we have to do is calculate this thing, the chi-square test statistic. What it does is it takes your observed data, subtracts the expected count from that data and squares it. This is already similar to the variance formula. And divide by the expected count. Now that's the difference from variance, but this is pretty similar by analogy. What this is trying to do is take a type of distance. The distance would be from the actual data you have to a different table, the data you expect to have if the null hypothesis is really true. If that distance is far, it'll be reflected here on the test statistic, and then again here on the p-value becoming really, really small. But if what we got and what we expected is very similar, well, the p-value becomes large and the test statistic gets small. It all comes down to then what is the expected count? That's like the superstar in all this. The expected count is by finding your sample size, the total sample size across all outcomes, multiply it by the ith population proportion, reflected here as pi naught, So one of these k different values, and you get your expected count. So it's not too terrible to calculate. But any questions, folks, with the methods here so far? Okay, we are going to come back to this, so we might as well take a screenshot. So we said it's not too hard to calculate chi-squared, nor is it to get the actual p-value. But what's nice about this is if you choose to, totally up to you, you can just make RStudio do all the heavy lifting for you. We implemented the entire test statistic process, p-value, by just using these two quick lines in syntax. It's kind of amazing in a sense. But what we didn't do was check the conditions, so let's start here. This was the problem from the first day of class. We saw a blip, and we were deciding, is that statistically significant? We didn't really have the language or the tools to really address the question, so we just kind of eyeballed it and made our own opinions way back at the day in chapter 1. So now we're ready to formalize it. The practical question is there any relationship between season and homicide? To determine that, we have to specify the parameters P1 through P4 as being the true proportion of cases of homicide, I should say that specifically, that land across these 4 different seasons. If there's no relationship, then the null would be true. There's an equal chance, a 25% chance, that any one homicide is categorized amongst the 4 different seasons. But the alternative would say there is something going on. That would mean at least one of these 4 equations fails, which would mean 2 or more fails technically, but we usually just say it in this way. At least one equation in the null hypothesis is false. So if there is a false one, probably has a lot to do with summer that went up higher. That means the other categories might have went down a little bit more, but this looks like it's the major reason why we have an issue here. But even though we have a p-value, we have to make sure the conditions are met. So here's where we're going to come back and actually check the conditions. So here they are right down for us to take a look at. Should clear this off now at this point. The tricky thing about the chi-squared procedure is it's really fast to get your p-value out. But when you're checking conditions, you have to do a little bit more digging. So what I would do for this is come back to your table right here. We need a total sample size. So you might just take all of these, add them together. But the problem did specify that there was 1,361 homicides. So that did give us a shortcut. And now we can say that the expected counts are, when we say expected, we mean the counts we expect to see if this is actually true, that those are the specific parameters for all these values. We will just take the sample size n, multiply by each one of these parameters, and that's what we get for expected counts. Let's write it in as a table just to kind of visualize it. I'll just say here, expected counts. I did not think this through. Let me make it look like a real table. So we've got expected counts going this way. I also need the seasons because there will be an expected count for every outcome of the categorical variable. So here's winter, spring, summer, and fall. And finally, the formula that was up above in the notes just said, take your sample size, 1,361. If we want the expected count for winter, you have to multiply by the parameter for winter. But all of these in this problem equal exactly 1/4. So we're just multiplying 1/4 by this and getting a count in every single one of these categories. So go times 1/4, and that's our expected counts. 340 at 1/4 of a homicide in every column. That always seems kind of strange to get a decimal answer on this one, but it is actually totally correct, even though you cannot have a single instance of a homicide at, say, 25% of a homicide. It would have to truly be integer values. The reason this is allowed right here is only because when we say expected, we mean when the null is true, and we mean after doing this study with that many observations multiple times. On average, if the null is true, this is what the counts would settle towards. So that really looks weird, but it's really a type of average going on. So what do we need? Well, for this to really work, the expected counts should not have more than 20% of these categories less than 5. We're okay because they are clearly well above 5, but we should still calculate these for the purpose of, say, the final exam question. Just for the sake of saying what would go wrong if condition 2 was violated, that would say, let's just temporarily say right here, we got maybe 4 expected counts in winter. Well, that's one category amongst 4. That would mean 25% of the expected counts is less than 5. That's enough right here to violate conditions. We can't use chi-square in that setting, since we would have more than 20% less than 5 in that case. So we're good on this route. But another thing to watch out for is if for some reason we got maybe just a 0.25 here, then it violates condition 3, where it says all of the individual expected counts must be at 1 or greater. So this causes some massive instability with our p-values. For this problem, these are really large counts, so we can say this shows the sample size is large enough. So for this to really be conditions that are met, we really have to have a simple random sample. Let's see if we have any indication from the problem. They don't always put it in the write-up. Let's see. The author is their season for homicide, classified those homicides. Yeah, nothing about randomization whatsoever. It's not clear how they got these. So we'll just say the conditions are met, provided these, and there was altogether, let's see here, 1,361 observations came from a random sample. The last bit is really just a disclaimer in a certain sense. But any questions, folks, on getting through the condition checking? Okay, well, let's put this away. We've done with the conditions, or maybe let's look at it just for a moment. Like we mentioned before, you don't have to say too much about the simple random sample. If you don't see any indication, you could just put down a disclaimer statement here. If you know it's random, you ought to say it, and you can now declare conditions are met. It's really right here we're going to really carefully check, but you absolutely don't have to worry about checking for the multinomial setting. That goes a lot above and beyond what we're actually doing in this class. So the work is pretty much done. We have a p-value. All we need to do is give a conclusion. But maybe let's do a little bit more on this one, just to show how to get chi-squared, how to get the p-value. Then we'll move on to the next question. So if we really want to get our value for chi-squared, here's how it would be calculated. We have to use the expected counts, the actual observed counts. Let's put that here just for a quick reference. And then chi-squared is going to be calculated this way. It's uppercase chi, so it just looks like the normal uppercase X. What we take is an observed count, 328. Subtract from it the expected counts. In this problem, they're all exactly equal, so we're always going to subtract the same value. It'll be minus 340.25, square that quantity, and then divide by that expected count, 340.25. So that would be our first chi-squared component, is how we would say this. And if we did, for some reason, maybe this is a different problem, and the p-value was low, if we do reject the null hypothesis, it's kind of frustrating because all we say is, we found evidence at least one of those equations is false. We have to say with the context, but that's not saying too much for our overall conclusion. But if you want to go a little bit further, it's these things you should be looking at. The larger of those values is going to tell you the reason, potentially, why you rejected the null. that's due to the largest components you're going to see here in this count. But let's keep on moving in. The next one is going to be, once I find the eraser tool, plus an observed count of 334 for spring. So we subtract from that the expected count, 340.25. Divide by the same quantity. And I'm looking towards spring, but again, all of our numbers are the same. But if this did change, we would change the same corresponding values right here. Almost there. Plus, next one is 340. .25, subtract from that, and square 340.25. Oh, hang on, I did make a mistake here. I should put in the observed count of 372. Shouldn't scroll and hide the data, that's not going to help out. 372, the actual observed count, then subtract from it. 340.25, divide by 340.25. And one last one. Kind of exciting, we might get this in one line. So last observed count is the 327 homicides in fall. Subtract from that, expected count for fall, 340.25. And then divide by 340.25. So that should be what it takes to get our chi-square test statistic. Leading a table is not an easy operation in Microsoft Word, it turns out. There it goes. Let's throw this into the calculator and just double check if we got the 4.0345. So now on paper, and even though our final exam is a take-home exam, one of the reasons to write this out is just to illustrate one more time. Even on the final exam, this is a good idea if you're going for partial credit. If you made any mistake in the calculator, that might be really hard for me to tell if you're on the right track or not. But on the final exam, I still grade this as if it was a real in-class exam. And if this is correct on paper, any number you put down here, no matter how wrong, you're still going to get a lot of partial credit. So let's see if we can get this in. 328 minus 340.25 squared, 340.25. This is kind of more of a test in patience to get this all exactly right. We have an answer, so let's see if we hit it. 334 minus 340.25. 340.25 divided in. 372 minus 340.25. Power 2 divided by 340.25. And then last one, 327. Let's see if we can fit it down here. 327 minus 340.25 squared divided by 340.25. After all that, hey, we got it. That's our chi-square test statistic. And we get even more accuracy here. This one's to 7 decimal places, but it's at 4.0345. I'll just carry the one that RStudio gave us. So here's our chi-squared, 4.0345. So that's the method of getting the actual test statistic out. But I'd say the major reason of doing this is it's just now fast and available once we are looking into the conditions. So after you do the condition checking, it's kind of up to you if you want to calculate by hand or let RStudio do the work for you. I think both approaches are just as easy sometimes. Here's the last step in the process. If you decide to do this by hand, the p-value would go like this. We'll take probability, then it's chi-squared. Let me double check that there's no dot between those. I always forget these functions, but if you just type it slowly, RStudio wants to tell you everything about it. Looks like that is the right function. So probability for the chi-square distribution, throw in the test statistic, 4.0345. Chi-square goes there. I forgot to square it, so I'll put that power 2. Next thing is a little bit tricky. You have to put in k minus 1, which means you might have to look up what the k is in this problem, but k is just the number of outcomes. Our categorical variable had 4 outcomes, 1 per season. So we would just put in 3. Let's put here just as a note. K is the number of outcomes. And beyond that, the last thing that you must do, no matter what's going on, if it's chi-squared, the hypotheses always go the same way. It's always an overall test, and no matter what, we put in lower dot tail is false. So that's the syntax to get the p-value. We're trying to get to 0.2578, just to double check if we're on track with our studio. So this is the moment of truth. Probability chi-squared, 4.0345. 3 degrees of freedom, lower dot tail set false, gives us 0.2577. That looks like this was rounded to 4 decimal places, so that's exciting. We have the p-value to even higher accuracy, but I agree to round to 4 as well. Let's call it 0.2578. So that's the nuts and bolts of the entire procedure. Any questions or comments, folks, so far? Okay, well, however we calculate, whether you go for our studio by hand, we'd still at this point look up our hypotheses. At any reasonable significance level, we are going to fail to reject the null hypothesis, which would mean we fail to conclude that this is true. We have to write it out using the context, so you probably want to be looking up to what you said the parameters were as well. So back down here for the practical conclusion, I'll just add a little bit more notes to specify this is greater than 0.05, which is equal to alpha, which means fail to reject H naught. Well, this is our penultimate hypothesis test, so standard reminder. However the conclusion goes, we can't say anything along the lines of, we found evidence that this is true. The closest thing you can say to that, which is still kind of a dangerous comment, is our data is consistent with the statement of the null hypothesis, but it's a dangerous statement because it could communicate you believe the null is true, which is not our objective. We have to say something more along these lines if you really want to hit the conclusion. It always centers around the alternative hypothesis. Our p-value is low, we say we have evidence is true, and if it's large, we fail to find the significant statistical evidence of this statement. But when it says using the context, it means we have to say what we meant by at least one equation, which means we have to go back to the parameters and say a little bit about what they represent. So a conclusion could go along these lines. These data fail to provide significant statistical evidence in support of the statement that, okay, it's already a long sentence. Let's take another look at here. We're saying at least one of those equations is false. That would mean at least one of these parameters is not equal to 25% chance. So let's say the statement that the percentage, let's see, how about, yeah, let's say percent chance of a homicide in any season is different than 25%. So that's about how we'd write out this statement. Here, it says at least one equation is false. That would mean one of these equations is not equal to a 25% chance. And we just wrote it in by putting in what some of the context was in the problem. I think the conclusion is sometimes kind of tricky with chi-squared, but the more practice, the more help we get. So we'll have another problem down below, another problem on the review we'll make sure to get to before we end class on Wednesday. But any questions or comments at all, folks, with what we put down here? Okay, well, we got it, folks. That's our penultimate problem of the entire semester, well, other than the review problems. And here is the last one for the course. After that, we're just reviewing content. So the major difference between example 1 and example 2 is all about the hypotheses. I kind of like these problems because they're really fun to set up. You just set all your parameters equal to each other. If there's 4 parameters, they would be set equal to a common proportion of a fourth. If there was 5 parameters, this would be equal to a 1/5 or 20% chance and so on. But chi-squared doesn't always line up in this way. Sometimes the probabilities you specify for every one of the parameters do have natural specific values. And this is a good problem to indicate this. If you were guessing genetics, you're definitely right. This is where a lot of genetics works get done. Chi-squared is a natural setting for assessing these kinds of problems. And there's a lot going on here. So if you're like me and you're just not up on biology and genetics, you probably want to read this a couple times. So let's do it ourselves and read at least once. It says here, if we focus on different characteristics of an organism, each controlled by a single gene and a cross pure strain having genotype AABB, with the pure strain having genotype lower a, lower bb, the resulting genotype will be this, uppercase A, uppercase B, lowercase b. So this is a lot of hard work in genetics to support that statement. And it goes even further by saying, if these first generation organisms are then crossed among themselves, a dihybrid cross, there will be 4 phenotypes depending on whether a dominant allele of either type is present. And actually a lot of growers take advantage of this. Some of the most famous apple trees, for example, are a result of the certain kind of cross where if you look at the offspring of these trees, the apple is totally different. It's not what you wanted. You wanted the original tree. Well, you have to go back to the very first cross. That's how you make that tree. And all of the resulting stuff might not be the apples you actually want. So genetics is really interesting. And it says here, Mendel's laws of inheritance imply that these 4 phenotypes should have those probabilities. And he worked really hard to establish that with data, if you've read his stories. So those are the natural probabilities that would go into any setting like this. And here's the next kind of setting. I have to admit that this data is nearing 100 years old, but it's still interesting data to look at for the purpose of looking at chi-squared. It says the article, and this was a real article back in the day, Linkage Studies of the Tomato, reports the following data on phenotypes from a dihybrid cross, putting us in the right context, of tall cut leaf tomatoes. They're specifying one genotype with dwarf potato leaf tomatoes, sorry, that was a hard word for me. That's the other genotype they're specifying. So we have 4 categories corresponding to the 4 possible phenotypes. And our null hypothesis is already specified. We're going to test this. Total sample size they give us as 1,611, so that's kind of nice. And these are the resulting data. So looking at these data, it almost looks like it fits, right? We have a large count for the larger probability. These look like they're in the same neighborhood of these probabilities. And we have a smaller probability with a smaller count. So it looks like the predictions are panning out. But never content to leave well enough alone, the people back in the day in 1931, they looked into this. They did a formal test, and we're going to do it ourselves. Any questions at all, folks, about the context? Okay, this is one of those weird problems where, again, we have to resist the urge to say the null hypothesis is true. We're not trying to prove Gregor Mendel's law of inheritance. We're just trying to see if this context shows that there's something else going on, which would challenge the genotypes of these leaves right here, because I trust genetics more than the classification of those plants. First thing we want to do is specify all the unknown parameters using the context. We definitely have a big hint because the null hypothesis was specified. When it says specify the parameters, we're talking about these. It's kind of just a generic statement, but we have to put it down just so we know what our conclusion is going to look like. Let's write out and say, let P1, P2, P3, P4 denote the true proportion of, now we can go down the categories. I'll write these as tall, cut, leaf, tall potato leaf, this is the tedious part of the problem, then dwarf cut leaf, almost there, dwarf potato leaf. I have to admit to you, I'm not sure what that would look like. And then we can say, respectively, for this dihybrid cross. Okay, so we've got our parameters down. That took a moment. The null hypothesis is already stated right here. So when it says state the alternative, that's the only one you would have to provide. Although you could put them both together if it just seems right. This will be the first time we just state an alternative all on its own. For me, I would possibly be tempted to say it this way, and I'm always going to leave it up to you. HA, PI is not equal to PI not for some I in, let's say, for some I with 1 less than or equal to I less than or equal to 4. So that's kind of a heck of a statement on all honesty. I'd say it's allowed because it is very precisely conveying what the alternative would be at every chi-squared. But if it makes more sense to you, you can just write it out like we did right here. At least one equation and the null hypothesis is false. I'm going to leave it entirely up to you. It's going to be more of you just determining what fits your writing. It's a stylistic choice more than anything. So let's go with this just to convey it is an appropriate answer as well. We're going to use a 1% level of significance. And so it doesn't hurt to just write this out. Alpha is 0.01. Good reminder just by doing that one little step there. Well, that's part A. We've got the parameters down on alternative hypothesis. Next thing we're going to look into is expected counts. Only reason to do that is we wonder if the sample size is large enough. It probably is, but when you see a small probability anywhere in your null hypothesis, it is a reason to worry. That could be enough to cause our problems, cause us some problems, but again, that's pretty large, so we're really just doing it to show what the steps would look like. Let's compute expected counts. We have to work with two tables. This one is the observed counts. So now expected counts go this way. We have 4 categories, and instead of writing these all in, I'll use the shortcut, it's just the index, I equals 1 through I equals 4. So abridged, I equals 1, I equals 2, I equals 3, and I equals 4. Now, because our null hypothesis has probabilities specified for each one of the parameters, you have to be a little bit more careful in calculating this. The process will always look like this. Take your sample size, whatever it is, 1, 6, 11. To get the expected counts for I equals 1, tall cut leaf, you have to multiply 1, 6, 11 by the probability 9/16. So if the null hypothesis is true, this is the number we expect to get. And it's, again, always weird that this is not necessarily an integer. Let's carry in 906.2. Rounding to the nearest 10th, 10th, I'd say, is okay and appropriate here. 906.2 here. because our main objective is mainly to look into conditions by doing this step. And taking a look, that's pretty in line with our expectations. So it looks like our p-value is probably going to be huge, but that just depends on what happens with the rest of these values. So let's do it again. You're always using the total sample size, and then now you're just moving to the next probability, 3/16. So that's going to drop it down to 302.0625. Because the next probability is still 3/16, we're filling in expected counts into two cells here. Let's call it 302.1. So last one, take your total sample size, 1,611, multiply it by a probability of 1/16, and looks like we're all set. This is the only one that had a chance to destroy our conditions, make chi-squared not work, but this is well over 100. Let's call it, say, 100.7. And so this would tell us that the conditions are met. They ask us straight away, does the data meet the conditions for the chi-square test? Well, I would say probably, except this is a really old data set. I'm not sure how they got their tomato plants from the dihybrid cross. So that's the only thing that's a question mark for me, is if these data, 1,611 observations, could qualify as being a random sample. We can at least assess and say all the expected counts are at least 5. That's a weird thing to say, because we could say they're at least 100, right? They're all quite large. But this is just the benchmark where we would have a potential issue if it dropped below 5. So we can say here, and so the sample size is large enough. We're unsure if this was random data at all. So you could just say here, again, as a fast statement, the conditions are met. Provided these data came from a random sample. Well, we're just about done, folks. All we need is now chi-squared, a p-value, and we're on our way. Any questions or comments to this stage? Okay, well, if you like calculating the chi-squared statistic by hand, it's not too bad. Just copy what we did before. You would be taking 926 minus 906.2, square that result, divide it by 906.2, and do it 3 more times for the appropriate cells going down the line. If you like RStudio, then you could just throw it all into RStudio. Let's try that route just to show for the first time today, at least, how that process will go. It's also a little bit different than in the first problem, because we have specific probabilities in our null hypothesis. So putting this in RStudio takes a little bit of extra work just because of that right there. So let's just show just how it should go. First thing we do is we need a new table for counts. So let's put in counts gets C to combine, and 926 we're just pulling from this table. 288, 293, 104. Next thing to store is your probabilities, and you could name this just about anything. I think I'd probably just call it prob for probabilities. Gets, combine. We want them in exact form, so 9/16 is the best way to input this into RStudio. 3/16, 3/16, and 1/16. So only way we can have a problem here is if you switch the order of one of these or one of these. So as long as everything is in its corresponding order, you're all set. Then it's going to be chi-squared dot test. Give it counts. And this is something I've had a problem with on RStudio before. Let me see if this happens again. give it prob, feels like the natural thing to do. You can run this whole syntax with Control A, Control Enter. And yeah, I thought that would happen. Didn't know how it works. So the natural thing you would try just falls flat on its face. Here's what's going wrong on the chi-square.test. You actually have to say right here, because of the way this function is developed, P equals probability to tell RStudio what to do with this column of vectors. The moment you say P equals right here, it will suddenly know what in the world that stuff is, and it calculates it for those given probabilities. So you really had to say that right here. That's the only thing that's kind of annoying to me about RStudio. Well, one of the things that's kind of annoying is these functions are not all necessarily consistent. You have to know your ways around them. Whether it's chi-square.test or t.test, there's some inconsistencies. But that's okay. This is free software, so I'll forgive them. So here's the entire outcome. You can take a screenshot if you like, or just select and copy should work just fine. Let's go that route. We did it, folks. I'd say, yeah, just highlighting it and copying it directly doesn't hurt. Let's also put in our syntax. So if you have a problem like this one, watch out for the step right here where it says prob. That's going to be the tricky thing about RStudio. But now that we're kind of talking about the final exam, we're almost there. One thing I still want to throw out is RStudio is not meant to take off points on your final exam. If there's a syntax that's not working, just send me an email. We'll work on it together. If there's a graphic you need, like a histogram or a box plot, but something is going wrong in RStudio, email me and I'll just send you that graphic so you can work with it on your exam. So for the final exam, don't worry too much. If there's a problem on RStudio, we'll get through it one way or another. The only thing I can't help with is telling you what procedure to use or stuff like that. So I can't say what goes into RStudio based off the chapter you're in. That you have to decide. But I'm always going to be very happy to work on anything that is not working normally in RStudio. Let's maybe put this somewhere where it's not too much of a bother. Now, again, that's a really large probability, but we're probably expecting it because you can just see right here that the counts we got versus the counts we expect are extremely similar. So it looks like those exact values of the fractions might be correct, but that's not all what we're trying to establish. That's the frustrating thing about hypothesis testing is we cannot prove this null. We're only looking for evidence against it. And the lack of evidence against it is not evidence that it's true. It just means we have not found that evidence. So our statement or our conclusion has to fall in those kinds of lines. So to support it, you probably want to look at all of this right here. We want to provide a practical conclusion, but we can now see exactly how that'll go. This is greater than 0.01, our significance level for the test. Almost didn't matter what you put here. If it's an appropriate significance level, that's a ginormously large p-value. So now let's say here for our conclusion, the sample data does not provide significant statistical evidence that, now there's a lot you could say here. This could be a sentence that just takes up the whole page, one huge multiple fragmented sentence. But if we want to be a little bit terse, let's plan this a little bit. These were the proportions for these various kinds of potato plants from a dihybrid cross. So as long as we're bringing in some of the context, I'm pretty happy with that. You don't have to bring in every single gram you see there of the context. So let's say we don't have significant statistical evidence that the potato plants from this dihybrid cross, I feel like I'm misspelling dihybrid. Let me see if I can fix this. Dihybrid, Let me know if it's still off. We'll go with that in the meantime. Have probabilities spelling is really hard today. Let me try again with this one. Probabilities different from those specified in Gregor Mendel work. I felt like for this conclusion, good idea to shout out Gregor Mendel. Looks like it was a big part of this problem. But you can say a lot of equivalent statements. You could say here, our sample data is consistent with the probability outcomes for this dihybrid cross predicted in Gregor Mendel's work. That's absolutely a correct statement. Just always be wary of that one. If you ever say your data is consistent with the null hypothesis, you should be really choosy how you're saying that so it's not misconstrued. Well, we did it, folks. That's the last hypothesis test of the entire semester. Congratulations, we've been through a lot. Any questions or comments at the moment? Okay, looks like we've got about a little bit less than a half hour to take a look at least one sample exam problem. My objective is to do as many of them as possible. And even if we don't finish them all, I will post those solutions to every single one of them. So when you're studying the final exam, you could go back to some of these documents and get some inspiration and some help from what we did in the past. So let me save this down. I think I saved it. And now we're in the review problems. Again, it was modified at 2:43 p.m. So apologies to anyone who printed these out earlier. I don't have the data files. I'm a little bit behind on typing these out. So I will be adding the data files to these shortly. And apologies for any typos you see in there. You can tell I was typing them fast potentially. We'll see how bad the wordings are. This is what the review looks like. At the very top of the document, I also showed you how I'm kind of writing the final exam. Essentially just taking about 6 questions altogether. They're going to be randomized. So a feature of this final exam is we have to decide what is the right statistical method before we launch into the problem. And this is how I did it. I just go into RStudio. I define a vector that looks like this. I'm going to sample from X at a sample size of 6. And all this is going to do is sample without replacement. And one thing that I put here, which is a guarantee, is I'm not going to cherry pick how this is randomized. And I didn't on this document either. If I run this once and it comes out as 1, 2, 3, 4, 5, 6, I'm going to let it stand just like that. So it'll be randomized precisely once. Oh, and here's the illustration of how that goes. So if I went with this order, it would have been problem 3, then 1, 5, 4, 6, 2, and so on. Then I changed the numbering to go 1 through 6 again. And that's how we're going to have randomization on the exam. So it'll be in a totally fair way, no cherry picking. Whatever RStudio decides, we're going to go with it. So that's what happened here on this document. We have 1 through 6 different problems to go through. They're mostly brand new problems, so things we haven't seen before, except for this one, and it looks like I copied and pasted. I couldn't come up with a good problem of this kind of context, so I just stole it from a prior problem. We'll try to analyze every single one of these questions, and again, when we come back on Wednesday, if there's one problem that looks like we really should do, we will absolutely do that one. And for me, the one I want to make real sure that we do is this one right here. So I'll put this in yellow just to make sure that we do get this one done on Wednesday. But let's start then at the beginning, problem number 1. I haven't done these problems, so I'm not really sure how these are going to go. It says here, a study examines chocolate's effect on blood vessels function in healthy people. Okay, so they're looking at what chocolate bars are going to do. In the randomized double-blind placebo-controlled study. That's important words right there. It means whatever conclusion you give, because this is an actual experimental design, it looks like a high quality one, your conclusions can be about cause and effect. You can say chocolate has caused this or so on, so on. In the study, they said 11 people received 46 grams of dark chocolate, which is naturally flavonoid rich, every day for 2 weeks, while the control group of 10 people received placebo consisting of dark chocolate with low flavonoid content. So the chocolate tasted the same to everyone, and that means there's no weird effects going on when they take a look at their blood. Let's put a page break here of our own making, but not like that. Participants had their vascular health measured by means of a flow-mediated dilation. I'm not sure what that is. Before and after the 2-week study. So they looked at what their blood looked like before they were taking chocolate or the placebo chocolate, and then after. It looks like they're measuring the differences in their blood. The increase over the 2-week period was measured, with larger numbers indicating greater vascular health. For the group getting the good dark chocolate, high in flavonoids, the mean increase was 1.3 with a standard deviation of 2.32, while the control group had a mean change of negative 0.96. Looks like their vascular health went down. That's interesting. With a standard deviation of 0.158. That's my first time reading these contexts, other than when I was typing it out really fast earlier today. So let's take a look at this. We want to give a complete analysis. Looks like we're doing a confidence interval. But the first thing we have to decide is, what is the method on this? In other words, anyone see what the variables would be for this study? Kind of hard to say exactly, but you know what I can guarantee is, if they say standard deviation or sample mean, you're almost certainly looking into a quantitative variable. There is a quantitative variable in there. And it looks like these values, the standard deviation, the mean, are relative to vascular health measure, the vascular health measured by a flow-mediated dilation. I have no clue what the units would be on this. But we can say here, there is one quantitative variable. Let's call it vascular health. So we definitely have that, but there is another variable in the study. Has anyone spotted what the other variable would be? This is definitely, I'd say, the trickiest thing about these kind of problems is deciding what the variable would be. But depending on your point of view, some people might have said two variables. One variable being vascular health for the people who got the dark chocolate, and another variable could have been the vascular health for people who got the placebo. Still, they got dark chocolate, so they're not left out, but they didn't have the active thing that they're looking for in that problem. So you might say that there is one quantitative variable, vascular health, or you might say there is another variable, which is categorical. And for this categorical, the outcomes would be, let's see here, the treatment group of getting dark chocolate and the control group. The control group was the one that received the placebo. And so now, well, in a certain sense, we have two independent populations. These people weren't used twice. They were diverted into two different situations. So this looks like this is a two sample T methods that we would be using on this problem. Does that make sense to folks on the situation on this one? Okay, analyzing the variables is definitely kind of tricky. We did that on the first day of class. But another way you could have decided it's got to be the two sample T methods we're using is if they gave you two sets of statistics. They gave a mean for one group, a mean for another group, and same with the standard deviations. That's enough for you to probably decide it's got to be this method right here, the two sample T procedures. And if it really is, then we should be able to specify the statistics for both samples. Let's say from right here, for the group getting the good dark chocolate, the mean increase was 1.3. Let's call that X bar 1. So for the treatment group, we have X bar 1 at 1.3. It had a standard deviation of 2.32. So S1 is 2.32. And these are measures of vascular health with unknown mysterious units that go along with them. Next in the control group. Oh, and it's just noticed right above that I just missed a chat. Sorry, Espen, I missed that one a few minutes ago. I got to get better at noticing there's a chat coming through. A good call. The type of chocolate was the other variable for this one. Absolutely. And for, they said the other chocolate, the mean was negative 9.6. So X bar 2 for the second group, negative 0.96, and standard deviation was 1.58. S2, 1.58. Next, we need to know a little bit more. If we're going to make this work for us, we also need sample sizes. So let's see where those are. Let's see. 11 people received the 46 grams of dark chocolate. So that was the treatment group. We can say sample size 1 is 11. And let's see. The control group had just 10 people. That's unfortunate. But this sometimes happens with human subjects. It could have just been maybe one of the 11 people had some kind of medical emergency. They had to drop out of the study. That's one of the reasons we just have to have a method that accounts for unbalanced designs like these, even though they are not ideal. So sample size 2 comes out as 10. Our variances are unequal, but we're not worried about that. Our overall method doesn't care about equal variances. That's not an assumption for our two sample procedure. At this stage, we're about ready to analyze the whole problem, and we'll be doing it using a confidence interval. This is sometimes one of the more confusing things on a final exam. If it says a confidence interval, we really mean that. We have to provide an entire confidence interval. We have to interpret it, and it also means there's no need to state hypotheses on this kind of problem. Just go directly for the whole confidence interval procedure, and you are on the right track. It says a complete analysis, but I will still on the real exam put down the structure of state, plan, solve, all that kind of stuff. It just makes it a little bit more tidy and easy to process. So let's just state it down here. State. What would be the practical question in this case? Well, because we're doing a confidence interval estimate, the practical question is more of a desire to just estimate a difference. We can say here, what is the impact of consuming? Let me start over. I wanted to say impact of consuming dark chocolate. But if you say impact, probably the natural question is impact on what? Well, our statistics are relative to vascular health, so that's what we're looking for. Let's start over and say, what is the impact on vascular health for people who consume dark chocolate regularly? So to me, that would be the practical question on this kind of problem. If it's a confidence interval, it's sometimes kind of hard to write this down. A hypothesis test has a question that's almost verbatim being said somewhere in the problem. But if it's a confidence interval, you're just looking for a measure of the difference between parameters if it's a two sample test. So your statement would probably be something along these lines. Next thing we do is we have to state the parameters Always a little awkward without actual units that go along with these, but we can still do the best we can. We're in the two sample t methods, so we need two parameters. Let mu1 and mu2 denote the true mean. True mean of what? Well, it would be for vascular health. I'll say it this way, the true mean measure of vascular health. However they measured it, they said with a flow-mediated dilation. Again, that sounds painful, just the way they say it. So that's going to be the true mean of vascular health for participants given flavonoid. That's a weird word. Let me take a look at it. Where to go? A good dark chocolate is what they said here. Flavonoid chocolate. And they didn't say none, but low flavonoid chocolate, respectively. So we don't need hypotheses since we're doing a confidence interval. Instead, we need to state a level of confidence. On the final exam, some of these problems will just straight out say, use this level of confidence, 90%, 99%. But if it looks like this one, this could happen on the real exam, it's all up to you. So I'll leave it up to you folks. Which level of confidence would you like to do today? I think someone beat Zachary the other week, a few weeks back, on significance level or confidence level. If you've got one for us today, Zachary, I'd be happy to accept it. Or from anyone else. Oh, we've got a chat come through. Awesome, let's go for 99%. Thanks, Zachary. We will estimate mu1 minus mu2 with 99% confidence. Okay, so now we know what we're doing. We're about ready to get to the mathy part of this whole thing. We're going to need all of these values right here. Sometimes this is probably the more important step of just organizing your information. Do it nicely the first time, and it's not so bad to get through the rest of the problem. What you wouldn't want to do is constantly scroll up here and just read and look up. It's so easy to get mixed up on what's what when you have to do that. Easier to just translate it into our own language of these statistics here. And now in the solve phase, because we were given just simple summary statistics, here they are. I won't ask you to do condition checking. I mean, condition checking is about robustness, and you need more information. You need to know how these 11 observations are distributed. Same with these 10 observations. So I'll say here, for condition checking, we will skip for summary data. Like in this problem, I don't actually have any of the raw values at either group. I'll be very clear on the real final exam. If we were to skip the condition checking, I'll just write it into the problem. But when we do need to check the conditions, you'll kind of know because your data looks like this, for example. We're almost certainly checking conditions for these kinds of values. Okay, so we're going to go right into the solve phase. Well, we have to calculate some really interesting things first. And not all these are very easy formulas. So a very natural process in doing the final exam is once you've decided on the right method, just go into Moodle You can use documents like this, choosing a statistical method to help you out. Go to the relevant chapter, chapter 18 for this problem, and it'll help you to decide the right method. All the information you'll need for calculating statistics and such will be there. And the first thing that we have to calculate is SE, the standard error, of the difference in means, x bar 1 minus x bar 2. It's been quite a while, so let me know if I forget one of these formulas. This one should be the square root of. It's all about the standard deviation. This is what we're estimating for standard error. It'll be a S1 squared divided by N1 plus S2 squared divided by N2. Filling in the information, we are squaring 2.32 then divide that result by 11. Next, square the value of 1.58, divide by 10. Then just jam that into your favorite calculator. So back in our studio, this figure will come out as square root 2.32 squared 11ths, 1.58 squared 10ths, and we've got a standard error of 0.8596. 4 decimal places is a normal amount to round for these kind of questions. So 0.8596 gets us on our way. Well, if you have the standard error, that's looking good because the confidence interval is just going to be x bar 1 minus x bar 2 plus or minus t star times the standard error of x bar 1 minus x bar 2. So we could definitely calculate the difference in means here. We just calculated the standard error. All that's left to resolve is the critical number t star. But getting that as additional steps, we have to calculate degrees of freedom. And this is probably the ugliest formula in the entire course. So let's just run through it. Any questions first before we take a look at that thing? Okay, this is the formula I would personally be the most nervous in forgetting, but there are strategies here to remembering it. One strategy is I rewrote that formula just to make an observation. The numerator for the formula the book provides is simply your standard error to the power 4. That's going to help with memorization tremendously. Not that it's something you have to memorize, but the more you try to get in your head, the easier it is to use all this stuff. So I'll put in here SE, x bar 1 minus x bar 2 to the power 4. Then the way to memorize the denominator is if you memorize 1/2, you've got the other half. You just change the subscripts. And I believe it goes like this: 1 over n1 minus 1 multiplied by s1 squared divided by n1 squared. And again, I feel like we're on the right track, but if this was a real exam, I would heavily encourage you to do this. Just double check it. Go to chapter 18. Oh, and I scrolled too far. There it is. Chapter 18 has everything you'd want. You could go here to a summary document. You could go here to everything that we've worked on. Let's look at the summary document. Usually this could be just fine. And down here, looks like I had a typo in a prior semester. That's in red. I'm just double checking for my own purposes as well. These are easy to forget. 1 over n1 minus 1, s1 squared over n1 squared. I think we're on the right track. At full disclosure, when I come to class and I knew this formula is coming up, I just sit there and try to memorize it before coming to class because it's not easy to always memorize all of this. So there's the next portion. All I'm doing is changing subscripts. And now we can plug in information and crank this all out. So numerator is standard error to power 4. I think I had it right on the document, but incorrect here. Highlight that. Definitely put in the power 4. So 0.8596. To the 4th power here. So if our sample size is 11, this will be a 10. Multiplying 2.32 squared, divide by the original sample size, so this one's an 11th, the entire thing is squared, and then we do it all over again. This one's going to drop down to 1/9. 1.58 squared. Divide by, it says N2 here, so the full sample size, which is 10. Square that whole result, and we just about have degrees of freedom. Now there is kind of a small internal check in here. That check is if we consider the variances, the standard deviations to be equal, then the degrees of freedom should be 11 plus 10 minus 2, somewhere in the ballpark of 19. Looking at our variances, there is a difference between them, so I'm not expecting very close to 19, just somewhere in that range. If you got 2, you're way off. If you got 79, way off as well. So it's nice to have a small amount of expectations, even though it's not perfect. So here's the moment of truth. Let's throw this all into the calculator once again. We've got about 4 minutes to make this happen. I think we might be able to get most of the way through this procedure. 0.8596 to the 4th power is the first thing to throw in. Let me move this control tool here. Divide the whole thing by, first set some parentheses for order of operations. 1/10 times 2.32 squared 11ths squared plus 1/9 times 1.58 squared 10ths squared, and then close parenthesis, and I'm getting about 17.6886 in degrees of freedom. This is a good one to carry 4 decimal places as well. The degrees of freedom never had to be an integer. That's kind of the weird thing about this. 17.6886. Again, that looks like it's about in the right neighborhood of adding the 2 sample sizes, subtracting 2. We have to make a modification because we never assumed equal variances. The more these are unequal, the further this is going to go away from total sample size minus 2. Nearly there, folks. The main struggle with this procedure is T star. But to get it, we can now say T star. The critical number for this procedure is go negative QT. We have to look up the level of confidence. I think this was set to 99%. Yes, there it is. So the thing I usually do is not think about it too hard. I just go 1 minus 0.99, divide by 2, and call that a day. It's just weird to make a arithmetic mistake right here and have everything else right. Next thing we need is the degrees of freedom. So this gets input in 17.6886. And that should do the job for us. So that's the confidence, that's the degrees of freedom. Now let's see what this all comes out to. Negative QT, on top of the T distribution at 1 minus 0.99 divided by 2, so 99% confidence. Degrees of freedom, 17.6886. And we get a critical number of, it's pretty large, 2.8843. So this is all of the work, really, the interesting work. In order to get the confidence interval, we now have the difference of means. We always had that. T star finally has been calculated. That's the hardest thing about this because you have to go through a different formula. And we already had the standard error. We don't have quite 2 minutes to finish this off, so we'll finish off this problem, give an interpretation of the result when we come back on Wednesday. Then after, I probably want to start with this one right out of the gate, since this is the new content, the chi-squared, we haven't had a lot of practice on. We should probably do that one first, just to support the final. Then I'll probably just go in order, unless anyone else has a particular question you all want to look at right away. But any questions, folks, with where we're at so far? Okay, well, have a great evening, folks. One more class to go, and then we'll nearly be there. Have a great one. Thanks, you too, folks.